I know. No, I actually went to Oh, really? I'm in the band. No, but you had to this team is like winning ways. So that's good. It is. Yeah, they're like bringing their flag. And it's like, yeah, it's like, you wouldn't think our school would be good at any of that. Yeah. So there's like 2 or 3 random teams from like all over the country just there to watch our team play. That's very cool. It's kind of like concessions were real busy. You run concessions. We run the concessions because basically athletics gives us a kickback. You run concessions for any concessions. Basketball. We don't run the football because we're on the market. Basketball, volleyball. Any like we had like robotic tents or like but it was 6 hours long. Your feet. Normally you have like 4 people show up for the women's game and you can do one more thing. But from basically halftime of the women's game, there was no time to take a break. I guess that's a good thing. Yeah. It makes for really exciting. I mean, it's the beginning of the year. I wish I went to last Thursday. Apparently last Thursday we played our number 2 conference and we won because they missed a 3-pointer. We won by 2. They had buzzer beater 3-pointer. So we won. Really disappointing for them, but they're getting the game getting exciting. It's good. Yeah, that was very cool. That's good. Well, okay. That's right.
All right. Let's start with the attendance. So, can someone remind us what we were talking about last time on Friday? A quick reminder. So, what we were studying on Friday? What type of connections? Yeah. So we were working on the balanced equations of the y and delta connections. We introduced both of them, and then we were trying to go into different set of cases for each. So today actually will be quite some completion to our work. So we'll be considering a few more cases, and hopefully by Wednesday we'll be done with this chapter, with this large chapter. I've posted a homework on Canvas. Did you all see that? I also sent an announcement to make everyone is aware that a homework has been posted. It's scheduled for 1 week. Actually, I spent a lot of time going over 55 problems in your textbook to choose the best 10. They should be quite complementary to the textbook questions that we solved. There might be a few questions that require some computational skills, like proof, or well, I think one question of them is like that. And the rest are quite typical questions. They are just to provide you with some training on how the problems could be in the midterms or in the final. Again, I've received multiple emails so far, even before the beginning of the semester, regarding the dates of the exams. Actually, today I received another email from MSU asking when are the midterms. They need to have a time for that because we'll do a lot of scheduling here and at MSU. So I think we'll stick to the dates on the syllabus. So our first midterm will be on February 28th. I think it's listed here. So let me just check the assignment with you all. So this is assignment 1. Yeah, I think I received a question from one of you about the problems. So I listed those problems. They are by the end of the chapter. And they are from the 7th edition, which is available on campus. And I tried my best to choose questions that are shared between the 7th and the 6th edition. So they are exactly the same questions in the 6th edition. But be aware, in the 6th edition, there is a section for exercises and then another section for problems. Those are all from the problems section, okay? But for the 7th, there's no issue. So our book is the 7th. You could find them easy there. And it's due by Monday by the starting of the class, by 1 p.m., okay? So make sure to get started on that. And if you have any question or concern, feel free to join my office hour on Wednesday. I'm typically online, so I would be there in case any of you came in or joined. So let me get back to the exam dates. So where's the syllabus? So the dates are listed here. This is what I suggested. So our first midterm will fall on a Friday. Regarding Fridays, I've received, I think, couple requests from you for some students who are doing some athletic activities and they do have training or games on Friday. So they are authorized on regular days not to attend. I waive the attendance for them. But if you read that document well, you should cover all the materials which is being studied in class during those days. For the exams, no. There's nothing like no show up policy for the exam. Those dates will be firm. I think based on your attendance, I have usually like 55, 56 about out of 57 attending every class, even though I'm having like 15 people on Zoom, which means even if some people are missing, they are still attending on Zoom, which is a good thing. But on the midterms, it's a sharp policy that we have to attend on time, okay? Because otherwise, we need to do a lot of scheduling for another exams, which is not possible. In any case, if any of you, it comes to be like quite impossible to do the exam on the exam date, let me know ahead of time. Because the only possibility that I will accept another exam is by doing it one day before the exam. So it could be like February 27 at some time, which I'll be able to schedule with the testing center. And that will be very firm. So I would say your midterm will be on Thursday at 3 p.m., let's say, if they tell me that they are available to proctor you and do those things. Because I don't have class time other than this here, okay? So let's try all to be ready for the exam. No matter how ready you are, just come in and try your best. And don't be worried about the grades. Okay, that's still better than having a 0 if you don't show up. Okay. So those are just my notes. I hope everyone, if he's expecting some urgent travel, to me it's like a conference travel or something like that. I'll keep you posted ahead of time. And in case you cannot attend for a real reason on those days, let me know ahead so that I can schedule with another office an exam for you a day ahead of that. Okay? The same applies to MSU students because actually MSU people cannot wait on me. I told them multiple times that I need some time to figure out when the exam should be, but they need exact dates, so I had to confirm those. Regarding attendance, I should remind everyone of the attendance policy. If you check Canvas, if you check your grades distribution or the allocation of points, there's no specific points for attendance and participation. And I thought that would be in the student advantage to have that as a plus for you above the 100. Because last year we were in some situation in another class in 5540 where by the end of the semester, few of you or few of the students were graduating, but they had an F grade in total. So we had to make a few difficult decisions at that time because they scheduled a meeting with me saying, this is what I got. I have to graduate tomorrow, but I got an F on this course. But adding 5% or 6% in total means I need to add for you 100 points somewhere during the semester, which is not possible because an exam would be out of 100 the midterm. I cannot put for you 200 or 300 points. And even some other people were like in less severe situations. Let's say they had they needed a few points for a B or a few points for an A. So we had to make some tough decisions, mainly with students who were failing the course or about to fail. So, and at that time, we did not have a track of attendance. So I thought tracking attendance is a good thing. So in case you need some help or some bonus, by the end, I can determine that based on your commitment so that it will not be an arbitrary choice for this person or that. I'm receiving a ton of emails actually from you regarding attendance. Like some of you are getting sick, they have some car inspection or power outages. I understand those incidents might happen, and they won't affect your overall attendance. If I see a pink blank once in a while in your attendance, this is fine. But if I see a series of blanks, which means like I think one of you did not attend any class last week. I'm not sure if he was online. But that would be harmful because another office from the university is asking me to track your attendance. And they asked me to check if you start attending, I'm authorized to drop you within 2 business days from the class. Because that relates to the fact that the Department of Education requires you, in case you are receiving any sort of financial aid, to attend, not just to enroll in a class. I think one of you is not showing up, and I'm not sure if he's getting to Canvas. I'll get a report of that later. So I recommend and I encourage actually everyone to come into the class and share, because as I'm still admitting everyone to Zoom, not everyone is entitled to have attendance on Zoom. That's why I typically ask MSU students to post that there so that I check them in. Other students, I will still admit them to the meeting, but I will not be taking their attendance if they were supposed to be here. So let's agree on that, and let's consider your participation and attendance as a reward. It's not something as a strict obligation, but it could be for the best interest of yourself. I just had to make those few announcements ahead, and we'll continue the rest of our lecture now. So, by the way, MSU people, type in that in the chat, everyone. I see more than 10 or 11 attending today. So we'll get back to our chapter now. So we have been discussing the balanced loads. What's a balanced three-phase load? Can someone remind me of that? Yeah.
Loads where each have
Equal impedances. Yeah, that's true. So any three-phase structure with equal impedances, we could consider that to be a balanced load, even though sometimes the voltage might go up and down, but typically it should be equal over the three phases. The different thing will be the angle. It should be shifted by 100 degrees, whether it's a positive or negative sequence. So for this structure here, we have actually a Y connection at the source. You see the voltages, the set of voltages, and the load is of delta format. Okay, you see the delta, and there's something interesting to see all the time actually, that typically in the phase side we see phase measurements EAN with small letters, while for the delta side it's typically to use the line measurements ICA with big letters. Okay, because as we have said that the delta does not have a neural end connection or grounding. Okay, so the best thing if we want to do some calculations on the delta side is to begin with the line values or the line measurements. So to obtain IAB, IBC, ICA, we can simply divide the voltages between those two nodes, and we talked last time how to do the measurements as a reminder for you from electric circuits. So it's typically dividing the voltages by the same impedance that we have, Z delta. So here we have an example. He gave us certain value for Z delta, which is 530, and he obtained the values of IAB, IBC, and ICA. And they came out to be quite balanced with some phase difference. So in case you don't want to use the formulas or certain formula to divide that, you can simply get IA, let's say, using circuit analysis. So IA is equal to IAB minus ICA. Okay? So as a reminder from circuits, those type of currents and voltages are vectors. So we should be able to know how to add and subtract vectors from each other. As a quick reminder, since I'm removing CA from AB, those points are canceled, okay? Because I'm subtracting two elements, and the common thing is A. The same applies for IB and IC. So you'll get here those values of IA, IB, and C, and those are determined to be the line currents at each line here, IA, IB, and IC. This is the current which is flowing into that delta connection to the whole thing. Actually, you don't need to memorize all that. If you just trace this figure, it's typically given sometimes. So just track the points. Let's see IC. So IC is coming like that. By KCL, we see that IC gets to the point C, and from there it's divided into two sections, ICA and IBC. So if we apply KCL here, which we reviewed last time, ICA would be equal to IC plus IBC. I'm forgetting the vectors, but that's fine. And then IC is equivalent to ICA minus IBC. This is an easy way, actually, not to memorize too many things. There's a lot of things that we could do just by looking at the figure. We should not really remember that IC is equal to ICA minus that thing. So if there's a possibility not to memorize things, that would be much better, because we have a lot of things here. And then we will find out that, let's make this question. Based on your assumptions, what do you think could be bigger, IC or ICA? IC, why?
Because it's not being subject to.
Yeah, typically the current which is coming into the whole circuit is expected to be bigger than any portion of current which is circulating within the circuit, unless the other branch is zero, it could be equal. So typically, the currents, if you make the calculations and you'd like to make a check up on your results, in this case, in the delta case, IA, if you compare those numbers by those ones, if you divide them by each other, you'll see a factor of radical 3 minus 30 degrees, which means IA lags IAB by 30 degrees, and it's equal to that value times radical 3, which typically more than 1. I think it's 1.7, which means IA is 1.7 times IAB. And the same applies for other cases. Here he will be tracing those values, and you could see that IA is typically larger than AB, and it's ahead of it by 30 degrees if you are taking this direction. Okay? So IA comes first and then IB, and it's bigger. And they all should sum up to 0. Yeah, here this is something important. Sometimes to make our calculations easier, it could be a nice thing if we have a delta connection to make that as a Y connection or so, because that sometimes could ease the calculations. Delta calculations seems to get a little hard if you have a Y source, okay? So, and it's a typical thing to make a conversion, but there's certain change that should be happening on your circuit. If you are given Z delta and you decided to make that into Z Y, okay, or star, you cannot put the same value from here to there. If this value here is Z, you cannot change that to that and leave it as Z as it is, okay? Because those two will not be equivalent. If you make the current calculations later, they will not be equal on both circuits, on any phase. So they started actually in a dump way, saying, let's calculate the current on the first circuit and let's calculate the current on the second circuit and make them all equal. So let's call this IA, and this one is IA prime. And they wanted those two to be equal. And they obtained the equation of each current in each circuit, I mean, and they made them equal to each other. So you see here that we'll be scratching the common things. Eventually, it came out to be that ZY should be equal to Z delta over 3 so that both circuits will be equivalent. Okay? So, which means that Z delta should be equal to 3 times ZY. So this is very important because sometimes you'll be given a circuit in delta, and it could be an easy thing to do to divide that impedance by 3 and transform your circuit into star, and that would make the calculations much easier. Okay? Here's this representation, which we were saying that a balanced delta load could be equivalent to this Y load by dividing each value by 3. Okay? Here's an example. A balanced positive sequence Y-connected voltage source with EAB equal to 480 is applied to a balanced delta load where Z delta is equal to 30 and angle 40. The line impedance between the source and the load is 1 for each phase. Calculate the line currents, the delta load currents, and the voltages at the load terminals. So, let's see the figures so that we understand what's going on. We were given a star source or generator side, and we were given a delta load, but he made a conversion so that he could use a star load. So you could see on the figure that he divided 3 angle 40 by 3 and he represented that as a star. So now we have two equivalent loads. So the good thing about that, so IA, which is coming from here, is the same as IA, which is going to the other circuit. Okay? You understand why that made the calculations more simple for us? Because if we had here that delta, that IA has to be divided for two components, which could make the calculations harder. So just by dividing the impedance, we got an easier circuit. And eventually, you could, after you get the voltage and current values for this star, you could convert them back for the delta form. So you obtain them in delta. And here we have one more addition, is that most of the time before, we considered this line to be a lossless line with no impedance, with zero impedance. Here, actually, this is not true. A typical thing is that we need to have some impedance for the transmission line. And here it's represented by ZL. So let's go over the calculation. We'll start by calculating a typical current IA. IA is equal to, by circuit analysis, what's the voltage which is being applied from this figure? Okay. Divided by, what's the impedance? ZL? Hello? Yeah. So, and Zy is given by, this is Z delta by 3, because we changed the circuit. So, we make this calculation, but there's something very important. We need EAN, but the question gave us EAB. We always need phase voltages for calculations. Okay? This is very important because typically in the questions you are given line to line voltages, not phase. So you have to divide that by radical 3. Let me see the initial numbers. Yeah. And you need to subtract your angle by, so V phase equal V line over radical 3, and you need to subtract 30 degrees from the angle. Okay? Always. Do not forget this thing, because typically in questions they give you line-to-line voltage, not line to phase. Okay? So he did that here. You make those calculations, and eventually you'll get IA. There's no need to recalculate IB and IC. You just add 120 degrees to this angle and subtract 120 degrees. You'll get IB and IC. Okay? So you just solve IA, and then you get IB and IC. If you make 3 calculations, you'll be wasting a lot of time from other questions. Okay? Then, let's see for the delta load currents. Typically, we've figured out that IB from our derivations before is equal to IA over radical 3 and angle 30. So whenever you got IA, you just put it in this equation and you get IAB from the initial delta circuit. And the same applies to the other two line currents, IBC and ICA. You just add or subtract 120 degrees. The voltages at the load terminals, which means here, here at this load terminal, and here, and there, right at the load, how much that would be? It would be Z delta IAB. Z delta is given in the question, and we've obtained those line currents from here. So obtain those values, and again, you add and subtract 120 degrees. So effectively, here you are making just 3 calculations, but you obtain another 6. Okay? So I will not talk about grading now, but typically it's a must that you do those three correctly, and then a little portion of the grade will be on the other two because you're not repeating those calculations. I think I don't know in this book why they put this section here by the end. It should be at the first, but this typically shows us how we could transform our circuit from the three-phase into a single phase. Typically, when we are dealing with three-phase circuits, we use the single-phase diagram to make a simplification of the circuit. And dividing the initial voltage by radical 3 and subtracting 30 degrees was a thing that we did in previous problem for that purpose, because it will be much easier for us to do the calculations on each of the phases. Okay? So here, if you'd like to simplify the problem, and actually this is what we did, for zy, you divided that by 3. It came out to be tan 40. For the source, it was EAB, so you divide by radical 3 and you subtract 30 degrees. The line impedance won't change, whether it's a single phase or three phase for now. Okay? Because a line is still a line. I cannot divide that by 3. It's not a load. So this is just a representation, and here's saying a standard industry practice where people, even if they are dealing with three-phase circuits, they take a single line diagram of that. Now we'll extend our calculations of powers into the three-phase balanced circuits. We did the same calculations before. All those type of powers, complex powers, reactive, active powers, we made them on the single-phase circuits. I hope you were reviewing them. So now we make some little extension to that to show what would change in the three-phase systems. So let's start with the instantaneous power. What's the instantaneous power? Can someone remind us? MSU people, what about you? No, it's not an average power. It's the power recorded at every instant. It's a time-dependent power, which varies instantly based on t. So we have VAN. We are using here now the phase voltages. It's radical 2 VLN, V line to ground. Why we multiplied by radical 2? To get the maximum value of the voltage, okay? We should remember those things. Cosine omega t plus gamma, which is the voltage angle. The same applies for the current with the angle beta. And then, if we'd like to multiply them both to get the power, we get this equation below. So we figure out that we get two components. One of them is time dependent and the other is quite constant. Okay? This is what we have obtained here. VLN times IL cosine, those are constants. No T there. This term is still time dependent and it will average to 0 because it's a cosine. No matter how large is the cosine thing here, if you have 100 terms, it will all go up and down. It will average at 0. Okay? So this is for just a phase. If we want to get for phase B and phase C, we'll do the same thing, but we will subtract 100 degrees from each here and add 120 degrees for each those there. And you'll get the same equivalent circuits, but here within the cosine, you'll have some shifting with 240 degrees. So for the three-phase, you need to add up them all together. PA plus PB plus PC of T. Okay? So adding them all together will give us quite a large average value multiplied by 3 here. And this is the good thing about about three-phase powers that we get times 3 the value. And the rest of the items will be cosine terms. So if you add those up all together, they will phase out because they'll be like that. Okay? Adding those three cosine terms will give us 0 because they are balanced and equally shifted by that angle, which means the P3 phase came out to be just a constant, not time dependent at all. Actually, this is a great advantage for three-phase systems. We did not see that in the single phase. We still had those cosines and sines there. And then, if you would like to obtain VLN, line to ground, it's just VLL over radical 3. So you could modify the equation here by multiplying radical 3 by VLLIL, which means we could calculate the three-phase powers either from the phase voltages or the line voltages. Both are equivalent. So here, the total instantaneous power delivered by the three-phase generator under balanced operating condition is not a function of time, but a constant. This is a very big advantage of the three-phase system. We get rid of all that time-dependent terms. Instantaneous power balanced three-phase motors. So we were talking about the generation side. So let's see what would happen at the motor side and the impedance loads. So what about the complex power? Can someone remind us about that? What's the complex power? I think of starting doing some quizzes.
J on it.
This is one part of the complex power. It should be more inclusive.
Goes to real power.
Excellent. Yeah.
Okay, there's imaginary.
Yeah. This is the summation quite of all the active and reactive power. It's the total representation of the power. So here we start with some phase measurements, VAN and IA. And then we are just typically using the same equation for the single phase. I hope people remember SA equal VA and IA star. No matter what those things are changing, it's still VI star, okay? So that's why I'm saying this is an extension of what we did in the past. So I hope people are trying at home how to make those because they will be quite needed for later. So if if V and I both have angles, we need to subtract them here because of the star element. And then we change from phasor to rectangular form. So we obtain that in terms of cosine and sine. So we did that for a one phase. It's SA. If we want to do that for the three phases, we'll just repeat that for 3 times and we add them all together. So we'll just see that those terms were multiplied by 3. Okay? It was just 3 SA. So do not do those calculations in the exam. If I ask you about the three-phase complex power, get a single one and then multiply the value by 3. We're done. And here's the representation that we all know. S three-phase is equal to P three-phase plus JQ three-phase. So this will be the real section, and this is the imaginary section, active and reactive sections. So the active section is equivalent to 3VL line to ground IL cosine gamma minus beta. And if we change VLN to VLL, we need to divide by radical 3. Is that true? So we will have radical 3 VLL IL, and the same applies for the reactive power. So those two are equivalent. So I get a question sometimes, when should I use this one or that one? Depending on the question. If you had the V line to ground, it's okay to use the equation above. If not, use the one below. It's just a radical 3 difference between the two. So what about the S value? It will be just if you do P squared plus Q squared, it will give you just this term here, radical 3 VLLIL, regardless of the sine and cosine, because sine squared alpha plus cosine squared alpha equal 1. Okay? So we'll just have that term which is associated with the angle. And its unit is volt ampere. Now, let's talk more about the balanced three-phase motors. I think I'm repeating the things here. So we'll have quite the same stuff. But here he's mentioning the balanced Y and delta loads, impedance loads, okay? So typically it's still the same. Like SAB here, instead of using, we said for those type of loads, we typically look into the phase values. Okay, for the delta, we prefer to use the line values because they are easier to hold. So you'll be just repeating the values, but here you'll be given with VAB and IAB instead of VAN and IA. Okay. We are using the line values that we were given. You repeat the same things for S, which is VI star and S3 phase, actually, and you'll get the same things. Okay? Same formulas. And then we get S equal P plus 3 plus JQ3. P and Q are the real and the imaginary parts. And S is this term here. Okay? We get rid of the sine and cosine components because it's being squared to 1. So here, I think I'm just repeating the things now between star and delta, but the equations are still the same. It just needs some focus of you to know what values I should put in here in this equation. So typically, I would say just write the equations down. This is the most important one. And then try to figure out to read your question and be aware what values do I have here. Are they the phase or what?
Are all of these equations dependent on being a balanced system?
I think so. We are still using, those were formatted and created based on a balanced system. For unbalanced system, we'll have other thing there. It's related to the fault calculations and stuff like that, where those do not apply anymore. Because in case we lose a phase of the system, it's not balanced anymore. So we have another representation called symmetrical components there, where you change the form of the circuit to another thing to be balanced again, and you redo the things there. This is in 5540 of last year. Actually, it's given now. It's being taught by Jian, but I'm still aware about that content. So we'll not see them here. Okay. Here's some example. Power in a balanced three-phase system. Two balanced three-phase motors in parallel. An induction motor drawing 400 kilowatt at 0.8 power factor lagging, drawing 150 kVA at 0.9 factor leading. So those are two loads, quite different. Our supplies is by a balanced three-phase 4160 source. You'll have a couple problems like those in your assignment. So I hope people would train on them. After solving this one, you should be okay. So first question, we have two loads, okay, connected in parallel. So they just add up to each other to be equal to the source. But what about this source? Is it, we just were given by a voltage value. Is it, what would you define that when you are trying to solve the problem? What's that value? Is it a phase value, line value? Yeah, definitely. This is a line value. Do not use it as a phase value. Your calculations will be less by radical 3 everywhere. Okay? So you have a few parts here. Actually, this is a good question for the assignments in the midterm. So draw the power triangle for each motor and for the combined motor load. We did that before. This should be easy. For the combined one, you just add up the two values and you trace the motor. Determine the power factor of the combined load. So you get P1, Q1, S1, P2, Q2, S2. You trace here and there the triangles. Let's say one is lagging, one is leading. They should come out like that. If I want the combined load, I should add up those two and see what the values will be given and figure out the angle and trace the total load. This is how typically I do it, but this is a very fast calculation actually. I'm just telling people now. So now he seems to be doing some power factor correction. So a capacitor bank is being installed in parallel with the combined motor load. What would be the value of the capacitive reactance required on each leg of the capacitor bank to make the power factor unity? So no matter what the total power factor came out to be, maybe it will be 0.8. He wants that to be 1. So what should be the value of the capacitance of that capacitor bank? So basically, we have to get the Q value of the capacitor bank, and then from there, we calculate the capacitance. I think it's equal to V squared over X, Q, and then you get that X value. Determine the magnitude of the line current delivered by the source with the capacitor bank installed. So this is at the ideal situation. Power factor is 1. You have that P value, Q value, S value, calculate the currents. So we'll be doing that. Here I explained everything what we do, but here we'll go over the solution. For the induction motor, you're given this P value, so you get S, as I've said here, S1, S2. You get P and Q for both motors. For the combined motor load, the power triangles are shown below. So this is the induction motor, this is the synchronous motor, this is the combined one. You just add up the values to make this combined one. The total came out to be like upper triangle, which means overall it's a lagging motor, even though the second synchronous one is leading power factor. For the power factor of the combined load, you just divide P total by S total. It came out to be 0.916 lagging. Okay? The line current, I, is equal S over radical 3V. This is from the equations that we have studied, where S is the three-phase apparent power. We have S of the total load. We have V, which is 4,160 volts. We divide by that, so we figure out that the current which is circulating out of the generator is 81.1 amperes per phase. And then to make the power factor 1, we would need to eliminate all this 234.6 kV because this is the current triangle. Okay, and this is the angle that I have. If the power factor is 1, which means S is equal to P, then this triangle will be aligned. Typically, this is a very ideal case actually, where S is equal to P here. This is all disappearing, the Q. So I would need to calculate Q equal 234. I take this value from here and I make the calculation. It's a three-phase thing, so 3V squared over X of the load. You make the calculation, X came out to be 221.3 per phase. Okay? And then with the capacitor bank installed, what would be the current now? So S changed. Now it's equal to P. Is that right? From here. Then you make the calculation again. The voltage at the source is still the same. So it seemed out to be that the current decreased, which is ideal, which means we are able to deliver the same power for less current. This is the excellent thing of power factor correction. And all generated power are effectively used. So this is a very good example actually to solve at home. I went over every section of it. It seems to be quite cumulative of the things that we did. So I think we are almost done with the, where's that 10 minutes? We are almost done. I still need 10 minutes less the coming class just to say what's the advantage and disadvantage of three-phase systems, and we're done. Let's see here. Scott. Dalton?
I not sign it?
No, I'm just asking. Is that you?
Yeah.
You just wave your hand. It's not. Chloe. You? Okay. Just raise your hand because many people are looking at me. Devon. Landon. Okay. Is there any question about today's class or anything? Okay. Yeah, what?
Your G.
Okay. We're good for today. What? You didn't sign?
Your work. Nice. Get you the. I just wanted 6:30. Oh, thank you very much. I have the 5th, but I don't have the 6th. See, I was the same way, and then I just found the 6th. I have a physical copy. Oh, yeah, physical copy? Yeah. What happens to the best of us? You have a good weekend, Mo?
Yeah, amazing. What about you?
Good.